Hello and welcome. In this video we are going to discuss the structure and physical properties, that is the boiling point, melting point, vapor pressure relationships of the different functional groups that you are going to study in your organic chemistry course. The possible or the different types of functional groups that you are going to have access to are as follows, just as a reminder, so that you are continuously reminded of the same. You've got your saturated functional groups, which are your hydrocarbons. So you've got your alkanes. You also have your alkenes as your non-saturated, and you've got alkynes. You have your alcohols, and you also have your haloalkanes. You then have your aldehydes, your ketones, and you have your carboxylic acids, and you also have your esters. Now you will observe that I deliberately wrote these substances in this particular order because you can move from the one on the left to the one on the right. In other words, if you take your alkanes, your alkenes, you can actually get them to convert them into your alcohols, your haloalkanes, or thereafter you can convert your alcohols into your aldehydes and ketones, and thereafter you can get carboxylic acids, and subsequently you can get your esters. So these nine different functional groups that are there, we should be able to explain the relationship between physical properties and the strength of intermolecular forces, that is your van der Waals forces, that would include your hydrogen bonds, dipole forces, induced dipole forces, etc. This here, if you have forgotten what these are, it is important that you go back to your and revise the information from your grade 11 notes, right? But from there, if you remember well, you should be able to explain based on the strength of the intermolecular forces that are there. So once you know the strength of the intermolecular force, or first you need to identify the intermolecular force present in a particular scenario, and then you look at the strength of the intermolecular force that is present, and then from there you should be able to say, okay, if it is strong, it would mean that it is going to require more energy, and then so the amount of energy thereafter you should explain in terms of the amount of energy needed to overcome those intermolecular forces, and then thereafter you would then be able to explain or to conclude the explain or conclude the type of, or the strength, or or the degree that is required to bring the substance to boil, melt, or the nature of the vapor pressure. So explain, conclude the physical property, meaning to say, to tell us what the boiling point will be, which one will have that higher boiling point, lower boiling point, and why it will have a lower boiling point or higher boiling point, based on the characteristics that you would have observed. All right, so it's important from your observations of the isomers to be able to look at two isomers and conclude which one is going to have a higher boiling point even though you may not be given those characteristics, but just by looking at the structural arrangement of the molecule, you should be able to then conclude that this isomer A must have a higher boiling point than isomer B because of, and then from there you would explain that. I'm going to give you examples of one of or some of these phenomena that we are talking about. In the example below, we are going to look at a question from one of the past papers. This is from 2013, March 2013, if I remember correctly. The question reads, the table below shows the boiling points of 4 organic compounds represented by the letters A to D of comparable molecular mass. In other words, the masses of these substances are more or less the same. So that is, well, that's what they mean by comparable molecular mass. If you have a look, the masses are not that much different from each other, and they're molecular, and therefore you would expect all of them to have similar boiling points. However, when you look at the boiling points that are given, they all have very different boiling points, and you can see that that's the data that's given, and so you would then need to explain based on the structure of the substances to say why each one would behave the way it behaves. So now we then look at the first question. So you've got butane, propanol, propanol, propan 1O, and ethanoic acid. And so when you look at all of them, compound A is used as a fuel in gas burners. So this is what your butane is used for. So this is just the story you're being told that is compound A in the gas, liquid, or solid phase at room temperature at 25 degrees C? Is it a solid gas or, um, or a liquid or a solid at 25 degrees C? Well, it's got a boiling point of 0 degrees C, so that means it has to be a gas at room temperature, so it's a gas. How do you know? Because it boils at 0 degrees C, so 25 degrees greater than 20 is greater than 0 degrees, therefore it's now in its gaseous phase. How will the boiling point of an isomer of compound A compare to the boiling to that of compound A? Write down higher than, lower than, or equal to, and refer to the molecular structure, intermolecular structure, and the energy needed to explain the answer. So butane, if you look at it, it's got how many carbons? Got 4 carbons. This is butane. Right, so it's got 4 carbons, and so you'd have your hydrogens. Now they're asking you for the isomer of that of this particular substance. So the isomer that you're going to have is going to be one that is going to be having a side chain. Now this side chain is branched, and because it is branched, it means the molecule is not going to occupy as large a surface area as the previous as the butane itself, and therefore what that means is that this has got it occupies a smaller surface area, so the forces are acting over a small surface area, so it is more compact. And because it is more compact, it means the intermolecular forces are going to be weaker in this molecule, and therefore you should expect it to have a lower boiling point than your butane. So it should be lower boiling point than the butane. And these are the reasons that we are explaining. So it's lower than the boiling point of that. It is more branched, so it's compact, and therefore it is more branched. So once it has got branches, the smaller the surface area that's going to have. So it's more branched, and therefore the intermolecular forces are going to be weaker than when it is the open or less compact um, structure of your butane, right? So less energy is needed to overcome these intermolecular forces, and therefore that is the thing that's going to happen. So it's going to be lower than, right? And then you look at the molecular structure, and the reasons include those. And then 4.1.3, using molecular formulae, write down the balanced equation for the combustion in excess oxygen of compound A in excess of oxygen. So 4.1.3, I'm just going to write it here, 4.1.3. So what you have is butane. So the formula for butane is C4H10 plus your excess oxygen, and the product of the combustion of your hydrocarbons is carbon dioxide and water. So you just balance that equation. When you look at that, you've got 4 carbons, and so if you're going to get 4 carbons, and how much oxygen do you have? You've got 4 carbons, 10 hydrogens. And so if you are going to have 10 hydrogens, if I put the 5O2 H2O here, I've got 10 hydrogens and 4 carbons. So the total number of carbons, 4, 10 hydrogens, 5, 50, that's 8 and 5 is 13, 13 and a half. So if I 13 over 2. So if I multiply everything out by 2, I'm going to end up having 2C4H10 plus 13O2 to give me 8CO2 plus 10H2O, just to get rid of getting a fraction of a mole. All right, and then 4.4, compound A has the lower boiling point than compound B. So compound A has a lower boiling point than compound B. They have the same mass, but they are different. Propanol is an aldehyde, and the other one is a hydrocarbon, which is an alkane. And then give reasons for this difference in boiling points by referring to the following: structural differences between the two compounds, and also in terms of the polarity. So what you need to look at, or what you need to be able to explain in this scenario, is that one, compound B, the functional group is a carbonyl group. So B has carbonyl group. And the carbonyl group is that. And this group is polar, right? So it's a polar molecule, and therefore the forces that are going to be holding it are going to be stronger. So it's got stronger intermolecular forces, therefore stronger intermolecular forces as compared to the London forces that are existing within the butane molecule, which are non-polar. And then 4.2, 4.2, it says consider the boiling points of compounds C and D. Give a reason for this difference in boiling points by referring to the intermolecular forces present in each of these compounds, in each of C and of D. So C and D, you are to give the differences in the boiling point. Well, compound C is an alcohol. So C is an alcohol. It's got an OH group, and then ethanoic acid. It's got a carbon oxygen, and then an OH group as well. So what you need to know is that compound D has 2 sites for H bonding. 2 sites for H bonding, which is your hydrogen bonding. So therefore the intermolecular forces will be stronger, right? So it will form dimers, and therefore so therefore stronger IMF forces. And then compound C has one site for H bonding, and therefore the intermolecular forces will be weaker than in the other one. 4.2.2, which one of the compounds C or D has a higher vapor pressure? Refer to their boiling points to give a reason for the answer. So when you look at D, we say D has got two sides, so D has got a higher boiling point. So D has higher boiling point. Therefore, it has a lower vapor pressure than C. And the reason for that is because it's got stronger intermolecular forces, and therefore that is why it's not going to boil as quickly as the compound C, which has got a lower boiling point. All right, thank you very much for watching. If you liked it, please share the video, like the video, and also subscribe to our channel. See you when we discuss the next one. Bye bye.